Hello dear students, welcome you all. In today's lecture, we are going to discuss liquefaction of helium, right? We are going to, uh, you know, understand how helium gas can be converted into liquid form. Clear? First of all, we must understand that how we can convert a gas into liquid form. Clear? So there are two ways of converting any gas into its liquid form. One is by applying pressure, and second is by reducing the temperature. Clear? Both the ways can be used if we want to convert a gas into liquid, right? So here, uh, the liquefaction of helium was first done by Professor H. Kamerlingh Onnes. Clear? In 1908. Clear? He was the first person who has liquefied helium. Right? I'm showing the pic of Professor Kamerlingh Onnes. Uh, yeah, right? He is Professor Hick Kamerlingh Onnes. He was the first person. He was a Dutch physicist who had performed several experiments, clear, to produce a very low temperature. Right? Basically, he was working uh, with the production of very low temperature. Clear? During his work, he was able to produce a very low temperature, and he was able to liquefy helium. No, what temperature is required to liquefy helium? So if we want to liquefy helium, then approximately minus 268 degrees Celsius of temperature, or we can say 4.22 Kelvin of temperature must be reached. Clear? So how this temperature was reached? Clear? How Professor Kamerlingh Onnes produced this much low temperature, right? So he used regenerative cooling method. Clear? Regenerative cooling method. Clear? Regenerative cooling method means it is the extension of the Joule-Thomson effect. We have seen in earlier lecture that in Joule-Thomson effect, we were able to produce a low temperature by throttling a gas from a region of extremely high pressure to the region of extremely low pressure. There is always a production of a low temperature. If the gas is having its temperature of inversion quite high, it is not less than the room temperature, then we will get a cooling effect, right? So if we repeat that process again and again, then that process is called regenerative cooling method. Clear? And in that way we can produce low temperature, right? So Professor Kamerlingh Onnes used this method, regenerative cooling method, to produce a very low temperature, and then ultimately he was able to liquefy the helium. He liquefied helium in 1908, and he was awarded Nobel Prize for this work, right? This was the great work done by him, and by using this entire mechanism, he was able to produce a temperature of the order of 1.5 Kelvin. Clear? Temperature as low as 1.5 Kelvin he was able to produce, right? Then after when he did all these experiment and he was able to produce such a low temperature, he also did another miracle in the history of mankind. He invented a very uh, majestic phenomena in the physics, that is superconductivity. Clear? Superconductivity. He was studying the behavior of different samples at low temperature. So he found that at a temperature of 4.2 Kelvin, the resistance of mercury becomes zero. Clear? This phenomena is called superconductivity, right? So Kamerlingh-Onnes was also associated with the discovery of superconductivity, right? And it is, I think, one among the greatest discoveries in the history of mankind, right? So this entire work was linked with each other. So in today's lecture we will focus on the method, the arrangement used by Kamerlingh-Onnes for the production of liquid helium, right? So I'm going to the apparatus that was used by Kamerlingh-Onnes. Although that apparatus was quite complicated, but we are here using the simplified version of it to understand the working, right? So you can see here we have taken this apparatus. This entire arrangement is a Dewar vessel. Dewar vessel is basically we can say a thermally isolated vessel, clear? A vacuum vessel in which there is no transfer of heat between the this system and the surrounding, clear? So this is Dewar vessel, right? In this vessel we have this pump to compressor, clear? And this is from compression, clear? It means initially what amount of gas is present here, it will be taken to the compression, clear? And then that will be compressed, clear? Then we will supply helium gas, clear, along with that to this compressor, and then this compressor will send compressed helium toward this side, clear? So the compressed helium gas will come across this, and it will enter this region, clear? Now you can see here, this is one spiral path, clear? This is second spiral path, and this is a third spiral path. We have three spiral paths. So when helium gas is it comes from the compressor and it enter this region, then it pass through this spiral path, clear? So when it pass through this spiral path, obviously throttling process takes place. Here there is a valve. Valve is not visible here. Here there is one valve, clear? B. From that valve this gas get throttled. So when it get throttled, its temperature reduce, clear? Then this gas enter from here to here, then it is taken to this path. Now again there is spiral way, zigzag way, and there is liquid nitrogen, clear? This liquid nitrogen, this entire arrangement is again connected to a vacuum pump. Why? Because we have taken liquid nitrogen there. Now normally the liquid nitrogen has a temperature of around 70 Kelvin, clear? So it means whenever this helium gas will pass through this region, its temperature will obviously come to this temperature. It will have enough time to go through this spiral path, and it will attain the temperature of 70 Kelvin, clear? Then after here again there is a valve, clear? There is a valve, clear? Through this valve again throttling will take place, and when the throttling will take place, again we must have a change in temperature. But one thing is very important here, that is of utmost importance, right? What is that? That is temperature of inversion of helium, clear? This is very important. This is why this process of liquefying helium is so difficult, because helium have a temperature of inversion of around 43 Kelvin, clear? So this is the main challenge. In order to get cooling due to Joule-Thomson effect, this helium gas must be having temperature less than 43 Kelvin, clear? Only then, when there is a throttling, there is a adiabatic expansion of the gas, we will get cooling. Otherwise we will get heating. So this is done by using this liquid nitrogen. But as I told you that the temperature of the liquid nitrogen in the liquid state is around 70 Kelvin. So how it is possible? So this is possible when we connect this part of this apparatus to a vacuum pump. Means this liquid nitrogen is under a very low pressure. So when the pressure is very low, the temperature of the liquid nitrogen is reduced. Clear? If the pressure is increased, temperature is increased. If the pressure is lowered, then this liquid nitrogen is now boiling under the reduced pressure. This is very important. So when the liquid nitrogen is boiling, means it is in the liquid state and it is ready to get converted into the gaseous phase. But when the pressure is low, then the temperature is reduced around the 40 Kelvin. Now when the pressure is around 40 Kelvin, so obviously when the helium gas will pass through this region, it will attain that much of temperature, around 40 Kelvin. So when then that gas throttle through this valve, clear, then this helium gas goes from region of high pressure to region of low pressure, and then the temperature of the helium gas get reduced. Clear? So once the helium gas reach here, clear, so its temperature is reduced. So then once again this helium gas is taken back, clear, to the compression. Clear? It is again compressed and then it is back taken to this side. Clear? Now its temperature is less than 40 Kelvin. So once again it is throttled here. Clear? Its temperature reduced to certain amount. Then it is passed through this. Clear? Then again it is throttled here. Clear? So when it is throttled again and again, it is allowed to expand again and again. We are getting regenerative cooling, and ultimately the temperature of this gas will reach the temperature of liquefaction. Clear? That is around 5 Kelvin, 4.22 Kelvin. So when this temperature is reached, we get the collection of liquid helium here. Clear? It is shown liquid helium. It is then getting collected here. Clear? So this is the way, this is the process by which we can convert helium gas into liquid helium. Clear? So this is the process of conversion used by Professor Kamerlingh Onnes. And as I told you that due to this work, he got Nobel Prize in Physics in 1913, because this was a very, a difficult experiment to perform because of this constraint. Clear? Because if we want to convert helium into liquid state, then this much of temperature must be reached first. Clear? Then we can convert that into liquid. Further, this production of low temperature lead to the invention of superconductivity. Right? So this is all about liquefaction of helium and regenerative cooling. Right? So thank you very much.